Today's class is on parse tree and ambiguity in context-free grammars. We will see a technique named parse tree using which we can represent a grammar. So after that you can see if the grammar is ambiguous or not. Ambiguous, we all know the meaning of ambiguous means if it can express more than one thing, it become ultimately ambiguous. Means we cannot say it is definite, right? It can come up with 2 or 3 outputs, means more than one output, more than one meaning. Now we will see what parse tree says. This tree shows clearly how the symbols of a terminal string are grouped into substrings, each of which belongs to a language of one of the variables of the grammar. As we have seen that we can derive a particular language or a string from the production rules given. Here similarly we will use those production rules. We will derive our terminal symbols from the variables given, and using those variables and terminals we will draw a tree. That is our job. In compiler, the tree structure of the source program facilitates the translation of the source program into its executable code by allowing natural recursive functions to perform this translation process. This is not the part of our syllabus, but when you will go for compiler designing part, there you will see that this parse tree is very useful, because when we write a source program, it will generate a parse tree, and accordingly it will be the compiler will execute it, right? There are some recursive manner, there are some derivation, type of derivation, many more things are there. We are not going to details in this course. Fine. Now certain grammar allows a terminal string to have more than one parse tree. This is the main benefit of parse tree. If you are able to construct more than one parse tree for a particular grammar, then you can say this grammar is ambiguous. Okay, so this parse tree is very useful in defining whether grammar is ambiguous or not. Right? And if this situation arises, it's not a suitable situation for a programming, because if you can derive a tree in more than one manner, the result will differ, but we do not want that situation to occur. Obviously we should design our compiler in such a manner so that result is fixed. So this parse tree is very useful to find out whether our designing is correct or not. If we have designed a grammar which is ultimately ambiguous, then our job is not done. We have to rethink of it. Okay. Now how to construct a parse tree? You will be given a grammar, namely G, which consists of 4 symbols, namely V, T, P and S, and this is a concept of context-free grammar. And how to design the tree? Each interior node is labeled by a variable in V. Each leaf is labeled by either a variable, a terminal or epsilon. Okay, so you can see that according to the grammar, whatever the production rules are given, we will replace our variable with that terminal. It can be a terminal symbol, it can again be a variable, and it can be epsilon as well. And here we have given an example that if an interior node is labeled A and its children are labeled x1, x2, x3, xk respectively from left, then these are the derivation rules. This is the production rules. Whenever we will see the example, the concept will be more clearer. Okay, now we will see an example. This is the example. It is defining one expression. Here from expression E, or say from variable E, we can move to I, or from E we can even move to E plus E. And these are the rules given, these are the production rules available. So one of the possible parse tree, if we want to derive I plus E from this grammar given, we can move like this. From E we can move to E plus E using rule 2, and again E can derive I using rule 1. So if you, it is very easily understandable. If we draw the tree, it will look like this. From E it is generating 3 things. One is variable, another is an expression sign, and third is another variable, and from E we can generate I. So this is an example how to construct a parse tree. Okay. Now here I have explained that how the tree has been drawn. You can just go through it. It is easily understandable. I have already explained it. Just go through the steps. Okay. Next example shows a tree for generating a palindrome, say 0, 1, 1, 0, using the production rules given in the left hand side of the slide. Okay. So firstly, we have to keep in mind our string should start with 0 and end with 0. Okay, our means ultimate motive is to derive a string 0, 1, 1, 0. So first rule that we are going to use should have 0 in both the ends. So firstly we will use the rule number 4. It is saying P is generating 0 P 0. So we have drawn it. Now in between we want another string 1 1. So how to do that? If we use rule number 5, 1 P 1, and after that if we put the rule number 1, that is P is generating epsilon, then our job is done. So our parse tree will be like this. Fine. Again, the explanation is given here, what rule we have generated and what are the steps we have followed to generate this tree. Just go through it once. Now what is the yield of a parse tree? If we look at the leaves of any parse tree and concatenate them from left, we get a string called the yield of the tree, and which is always a string that is derived from the root variable. So if a parse tree is given to you, you can easily say what the string this grammar is generating. We have to do nothing. We have to just learn, or we have to just copy the leaf nodes starting from left to right, and this is the yield, means what is the output of the parse tree we are generating. Okay. Next is, say we have to derive one string, namely a star within bracket a plus b 0 0 bracket close, using the grammar that we have seen in as example 1. So if you follow the steps, all the steps are written here. So first what we have to think of, we have to bring one star in between. In left part of the star will contain one a, and right will contain a form, namely within bracket e plus e. So we have to move accordingly. So in the left, firstly we can use the derivation from e, we can move to e star e. So we can generate one star in between. After that, for the left part, from e we can move to I, and from I ultimately we can move to a. So our left part is done. For right part, what we can do, first our job is to bring two brackets, one is open, another is closed, and a e in between, right? So this can be done in the manner e can generate e within two brackets. Okay. After that, we have to bring one plus in between. So from e we can use the rule e plus e, so a plus will come in between. After that, at the left side of the plus we have to bring one a following the same manner, and in the right hand side we have to generate b 0 0. You can just see the production rules available and can replace accordingly to bring whatever form they are asking. Fine. Now what will be the yield of this tree? We have to move from leftmost leaf to our rightmost leaf. Fine. So first leftmost leaf is what? A, then star, then open bracket, then a, then plus, then b, then 0, then 0, then closing bracket. So this is the yield of the parse tree. Okay. Now this is the most important part, and this is ultimately you can see it is the goal of studying the parse tree. So we will define what ambiguity is. Sometimes a grammar can generate the same string in several different ways. Such a string will have several different parse trees and thus several different meanings. This result may be undesirable for certain applications, such as programming languages, where a given program should have a unique interpretation. Right. So if we are designing a grammar or a context-free grammar, ultimately it will be the need of a compiler to convert the source code into its executable form. So if we have designed a grammar in such a fashion that it is having different meanings, so it will be a disaster, right? So our program will never work accordingly. If we can generate a grammar which can guarantee us that it will give us a fixed result, our programming will work like this, then only our job will be done, otherwise not. So you can do like this. If you designed a grammar and you can generate a parse tree, if you got confirmed enough that okay, this grammar is not ambiguous, means whatever grammar you have generated, it is having a single parse tree, no more parse trees are possible. Okay, so in that case you can say your grammar is not ambiguous. You can move with it. We will see how a grammar can generate more than one parse tree in the next slides. Fine. We are again considering example 1. Here our job is to derive the string e plus e star e. Okay. Just see the two different way where we can generate e plus e star e. First, we can use rule number 2, that is e can generate e plus e. After that we can replace the second e with e star e. But in second case we are doing, firstly we are replacing e with e star e. After that we are replacing the first e with e plus e. So see, the result is same, but we are following two different approaches. Here you cannot see the difference in result, but if we replace this e with some values, our calculation will be different. Okay, we'll see it later on. Here just see, if our equation is like this, that is first e is equals to 1, second e is equals to 2, and third e is equals to 3. So if we follow the first one, what it says, firstly we are replacing e with e plus e, that means, and then second e with e star e. So we can say it is forming two different groups, first e and second e is being replaced by e plus e star e. So it will be, if we evaluate it, it will give 1 plus within bracket 2 star 3, which results 7. But if we follow the second approach, it will give 9. So can you see what is the danger lying behind this? If you can generate two different, more than one parse tree for a particular grammar in deriving a whatever expression they are asking for, so my grammar is ambiguous and it is dangerously giving two different results. So this is the most important application of parse tree to check whether the grammar is ambiguous or not. Now here we are again designing two different trees, say e plus a star a, and the parse tree will look like this. So if we replace first a with 1, second a with 2, and third a with 3, you can see that two different parse trees can be drawn, two different parse trees can be generated, and you can say this grammar is ambiguous. Fine. And now what is the difference between ambiguous and unambiguous? We have so far we have learned very well what ambiguous is. Now if my expression is like this, e can derive e plus e, means if we have to generate a string a plus b, put whatever the value of a and b you like. We are following two different approaches. See, in the first way we are replacing e with e plus e. In the first one we are replacing the first e with I, and after that we have replaced I with a, and again we have replaced e with I, and after that we have generated a plus b. But in the second line, or in the second way, we have replaced the second e instead of the first one, but ultimately the generation is same. So whatever values you put for a and b, our answer will be same. In this case you cannot say the grammar is ambiguous, since using it may have two different approaches, but ultimately it is generating the same result. So this, then it will be treated as unambiguous grammar. Okay. Now the two examples above suggest that that is not a multiplicity of derivations that cause ambiguity, but rather the existence of two or more parse trees. In general, whenever you will solve examples on the testing of this ambiguity and unambiguity of context-free grammars, you can easily see that if you can construct more than one parse tree for any of the strings generated, for any of the results you want to calculate, then you can definitely say that grammar is ambiguous. But if you cannot draw more than one parse tree, you can say the grammar is unambiguous. So this is so helpful, this parse tree is so helpful. And with this we will conclude today's lecture. Next class we will learn very important topic of context free grammar, say push down automata. Thank you.